Hey guys, it's Nilesh. In this tutorial, we'll study the remaining part of the architecture, and that is the execution unit. Here is a base diagram of the execution unit. It consists of 6 main parts, namely general purpose registers, special purpose registers, arithmetic and logical unit, operands, flags, and the instruction decoder. Execution unit performs all arithmetic and logical operations and also the internal data transfer operations. First, we'll start with these general purpose and special purpose registers. These four are called as the general purpose registers. These four registers are available for the programmers. Each general purpose register is divided into two parts, that is AH and AL, A high and A low. So combining them, we get AX register. Same way BX, CX and DX also. Each register is divided into two parts, 8-bit of each, so making a whole register as a 16-bit. Programmer can use this AH or AL independently or AX independently. Now what does this AX, BX, CX and DX does, we'll see, which is divided into A high and A low. They together can hold the operands and the results in the multiplication and the division operation. And they perform as a accumulator in string operation. You will come to know what is accumulator and all that later. For now, just remember these operations. BX register, which is divided into BH and B low, B high, B low, and it is used to hold the offset address in the indirect addressing mode. Third one is CX, that is CH and CL. CX registers holds the count. Just remember, it holds the count in the operations. In operations of microprocessor like loop, rotate and shift, all these operations requires a count to be set, and this count is held by the CX register. If it is a 16-bit count, then we use a CX register, and if it is a 8-bit count, then we use either of CH or CL. DX register, DX register is used with AX register to hold the 32-bit values in the multiplication and division operation. Also, it does the operation of holding the address of IO ports in the indirect addressing mode. This was about the general purpose registers. Now back to the second part. This is over. Now special purpose registers. Special purpose registers are the registers which does the dedicated task or user cannot change their use. They are defined for the specific use. The first one is the stack pointer, second is base pointer, source index and destination index. These are the four. Each of them is of 16-bit, and here the division like general purpose registers does not take place, so we cannot divide SP, BP, SIDI into two other parts. We have to use them as it is. The first one is the SP, that is stack pointer. Just for the revision, this is the structure of stack which works on the principle of LIFO, that is last in first out. 1 2 3 4. The address of the last value in the stack is held by the SP register. that is stack pointer, also called as the top of the stack. Stack is present in the stack segment, or stack segment, which is shown by SS register. To calculate the physical address of this 4, we need the segment address, and second thing we need is offset address. Now, as I said, offset address is held by the stack pointer, and stack always resides in the stack segment, so segment address will be given by SS register, which is present in the BRU, and offset address, which is held by the SP. This will give me the physical address. Now, to get the exact physical address, we need to multiply the segment address by 10h. There was a formula. Check out last tutorial about the BRU, and you will get the physical address of this 4. In this way, SP works, and SP holds the offset address of the stack. Now, second register which we have is BP, that is base pointer. Consider this is a stack 1, 2, 3, 4, and my top of the stack is over here, that is SP. SP is holding the offset value of this 4. Now, if I want to access this 2, then my SP should point over here, that is on a 2. To make the SP to point over 2, first I have to remove this 4, then this 3, then my SP will shift over to 2, and I will be able to access this 2. But without removing all this, I can access this 2, that is by using the BP. Base pointer is a register which can hold any random location in the stack. In stack segment, we have 2 registers to hold the offset address. One is SP, which holds the top of the stack, and one is BP, that is base pointer, which holds any random location. So in this way, stack segment is defined. All these points are discussed previously in the tutorial of memory segmentation, so you can correlate the things. Now, next thing is SI, that is source index, and last one is DI, that is destination index. Source index does the working of holding offset address for the data segment. DI holds the offset address of extra segment. These both can be used for any other segments also, but for that we have to do the segment overriding. And now both of them performs one more important operations in the string operation. Say that there is a string, one string, and we want to move it to another location from one location. Say that this is a string located at 1 0 0 0 0 h 3 4 5. Okay, and we want to move it to another location. That is 10101h. Now we will transfer this string from one place to another using the string operation. Now, offset address of this old location, that is source location, is held by the register SI, that is source index. So it holds a offset address of source, and the offset address of this new location, that is the destination, is held by the DI register. So it holds the second operation is holding the offset address of destination. So these are the special purpose registers. Done. Small revise on each of them. SP holds the top of the stack. BP used to hold the any random location in the stack. SI used to hold the source offset address in the string operation and the offset address of the data segment. DI offset address of the extra segment and the offset address of the destination in the string operation. Now the next is ALU, that is arithmetic and logical unit. This unit does the 8-bit and the 16-bit arithmetic and logical operations. And as we have seen, 8086 has a 16-bit data bus. That is, it can access 16-bit data in one operation. And the second thing is it has a 16-bit ALU. So these are the two main reasons why 8086 is called as a 16-bit MUP. ALU is over. Now next is operand registers. Operand register is a 16-bit register used by the control register to hold the operands temporarily. In the 16-bit operations, operands are needed to be held temporarily, so that work is done by the operand register, and this operand register is not available for the programmer. That is, normally we can't use it. So the operand register is over. Now next is instruction register and the decoder. They both are present in a control system or a control unit. Here is a queue which is present in BRU, and where all the instructions get stored in a queue. Control system fetches one instructions from here and decodes them. Now the fetch opcode of the instruction is stored into the instruction register. So opcode storing is done in the instruction register, and after storing the opcode into the instruction register, decoder is used to decode this code and send the control signals to the control unit. So the fetching and the storing is done in the instruction register, and the decoding is done by the instruction decoder. So in this way, instruction is fetched and the decoded. This part is finished. And the last one is a flag register. Flag register itself is a big topic. We'll see it in detail either in this tutorial or in next. Just have a quick look to the theory of the general purpose register and the special purpose registers. These are the general purpose registers and theory related to it. Just read it out. And this is the theory related to the special purpose registers. Thank you guys for the watching. Don't forget to like, subscribe and comment. See you in the next tutorial.